Quite often when we are looking at things that are changing, we want to know how fast they're changing based on some other variables change. And that's what we refer to as related rates. So we'll look at some examples shortly, but first thing I want to do is look and see the process of solving word problems, because quite often related rates are phrased in the form of a word problem or in actual application. They're models that we need to create. So as we look at these sorts of problems, here are the questions we may want to consider. So first thing we always want to do is have an overview of the problem and its goals, right? So to make sure we understand it. Then go and find an inventory of what information I'm given, what resources I have available to me. Then organize that information, solve for what we're looking for, and then check our answers. So it's generally how we would approach any word problem. But in case of anything where we're looking at related rates, it becomes a little more crucial for us to make sure we kind of follow a certain process, right? So to start with, when we talk about the overview of the problem and its goals, there are a couple of questions we want to ask ourselves, right? So have this internal conversation with ourselves. The first question I always want to ask myself is, do I understand the language and terminology, right? Because if I don't know what the words mean, I won't be able to comprehend what the problem's asking and start solving it. So to start with, that's the first thing that needs to happen, is I have to make sure I fully understand what the language and terminology that's been brought up mean. And then, do I understand concretely what I'm asked to find or what I need to find? And the standard that you want to apply to that is whether you would be able to explain it to a peer, right? Because if I can explain it in my own words to a peer, then I can probably feel safe enough that I understand it concretely. Okay, so let's consider an example. And we're going to go through this process with this example. So a 6 foot tall man is walking away from a 10 foot tall light post at a rate of 4 feet per second. At what rate is the shadow growing when he is 17 feet away from the pole? And at what rate is the tip of the shadow moving? All right, so again, the first thing we want to do is make sure we understand what this problem is talking about. I know we all understand what it means to have a 6 foot tall man walking away from a light post. But in this case, probably having a picture might help us have a grasp of what it means for the shadow to grow, right? So a quick drawing, and excuse the poor drawing, but that's basically the model that they are describing. So we have a man walking away from a light post. The light post is taller than the man, and what happens is we end up with a shadow on the ground created by the man blocking the light, right? So the shadow would be in front of him, and as he walks away from the light post, the size of the shadow changes, and it's going to keep getting longer and longer. So we want to know how fast the shadow is growing. And then the second part, as he moves, the shadow grows and it moves away from the light post because the man is moving and the shadow's in front of the man. So we want to know at what rate the tip of the shadow is moving. And we'll come back and look at that in our calculations. So again, just to make sure we labeled this properly, we are looking to know the rate of change of the length of the shadow, right? So how fast is this shadow growing? And this length would be the rate of change of the tip of the shadow's movement, right? So one of them is the length of the shadow, and the other one is how fast the tip of the shadow is moving away from the light post. Okay, so I'm hoping at this point I have a pretty good grasp of what they're asking me to find. I've kind of digested the information that's given. So next thing we're going to do is take an inventory of the resources that are provided. And what do we mean by that? Well, are there any formulas or diagrams provided? Well, in this case, there weren't any formulas or diagrams provided. We drew our own diagram, but there was not one that I was given. Can I find them somehow? Or can the given information be used instead? Right? So those are the questions I kind of want to ask myself. So let's go and re-examine this problem one more time. Right? So we already established they hadn't given me a diagram, but we drew one. So here it is. Next thing I'm gonna do is convert this into a more mathematical format. So I'm gonna change this into a pair of triangles. Right. So now I have a diagram, and I can see that there was a bigger triangle created by the light post and the tip of the shadow, and a smaller triangle that was formed by the man and the shadow. Right? So next thing we're going to look at is how to organize the information that was given. So what do I already know? Are there any quantities that I know? Are the equations that allow me to relate those quantities? And kind of look at our diagram and maybe label it in a better way, and see how I can connect the things that I know to what I'm trying to find. Right? So can I combine equations to get from what I know to what I'm trying to find? Right? So those are all the things we want to think about as we go through this process. Right? So going back to our problem one more time and putting the information in our picture. So this is the set of triangles that we had. We knew that the light post was 10 feet tall. The man was 6 feet tall. And there on the bottom, I have two pieces that I don't know. We'll call one piece A and the other piece B. Right? So notice I am told that the man is 17 feet away from the pole, right? So if this is the man, I am told he is 17 feet away from the pole, except that length is not a constant. So that length keeps changing. And as I label things in my diagram, I am only labeling things that are constant. The length of the shadow is always 10 feet. The man's height is always 6 feet. But how far away he is from the light post is going to change because he's walking away. And the length of the shadow is going to change because, again, the shadow is going to grow. So I've labeled it. I know B is going to be 17, but notice I put in the parentheses because that length is going to change. Right? So what other information have they given me? They've told me the man is walking away from the light post at a rate of 4 feet per second. So B is growing at a rate of 4 feet per second, right? So that's a rate. That's dB over dt. And notice we use t here for time. That's the rate of change of B with respect to time, because we have feet per second, right? So the denominator is time. The numerator is the length, right? So dB over dt, and that was given to be 4 feet per second. So I've written 4. I am asked to find two things. One, how fast A is changing. That would be dA over dt. So that's the first thing I'm asked to do. And the other question I'm asked to find is at what rate is the tip of the shadow moving? And if you recall in our picture, we had decided that this entire length is how the distance from the tip of shadow to the light post. So as I say, at what rate is it moving? I want to know at what rate b plus a is growing, right? So that entire length. So d of a plus b with respect to t. Okay, so now that I know what I'm trying to find, so there are a couple derivatives I am trying to find, and there is a derivative that I'm given. So what I need to do is establish a relationship between the lengths that I know, 10 and 6, and a and b, which are the piece that I have the rate for, the rate that I'm given, and the piece whose rate I'm trying to find. Okay, so that brings us to an equation that I can write. So we can set up a ratio here, a proportion for these triangles, right? So they are similar triangles and a proportion would work. Now, is a proportion the right answer for every problem? No. I have right triangles. Sometimes trigonometry or setting up a tangent ratio would be the appropriate thing. Sometimes the Pythagorean theorem would be appropriate. You kind of have to look at the information that's given and the relationship between what's given and what I'm asked to find. So in this case, no angle information was given, nor was I asked to find any angle information. So chances are I would not need to use the ratios like a tangent ratio or something like that. And I'm not using Pythagorean theorem, even though these are right triangles, because the hypotenuse is of no interest. Right? So a similar triangle ratio in this case would be the correct way to set this up. So we've set up a ratio of the sides of the small triangle, a over 6, to the sides of the bigger triangle, which would be a plus b and 10. Right? So a over 6 equals a plus b over 10. Right? So the next step, now that I have an equation that I can use, is trying to solve for the unknown. Right? So the question I want to ask myself at this point is, can I solve for the unknown quantity in terms of things that I know? Right? So going back to the information that we already had established, we had decided this is the equation that might work. So I am trying to find the derivative of a with respect to t, and I am given the derivative of b with respect to t. So this equation should work. I already know the rates of b, so if I took the derivative, those would be the two rates in this equation. On one side, I would have dA over dt. On the other side, I would have both dA over dt and dB over dt. And one of them I know, so I should be able to find for the other one. But before I go ahead and take the derivative, I'm going to clean this up just to make my life a little easier. I'm going to cross multiply these. Get 10a equals 6a plus 6b. Put the a's on the same side, so subtract the 6a. From this side to that side, I get 4a equals 6b. That allows me to then go ahead and take the derivative of both sides. So on the left side, I have 4 dA over dt. So we're taking the derivative here implicitly. We're thinking of both a and b as functions of time, right? So you can think of this as f of t. On the other side, this would be g of t. And we're taking implicit derivatives here, right? So this would be 4 f prime of t, and the other side would be 6 g prime of t, right? So they're different functions of time. Both a and b change. They're dependent on on time, and time is our independent variable, right? So this is what I get when I take the derivative implicitly. The next thing we're going to do is replace dB over dt with the value that I am given, which is 4. So I'm going to go ahead and replace it with 4. So I get 4 dA over dt equals 24, which is 6 times 4. Divide both sides by 4. I get dA over dt is 6 feet per second. So that answers the first question. Next, we're gonna have to find the rate of change of A plus B, right? And so this is a summation of two functions. I'm taking the derivative here, and the derivative over the sum. One of the properties is that I can distribute that in a way. I take the sum of the derivatives, right? So I'm using the word distribute here, not as a multiplication, but I can change the derivative of the sum to the sum of the derivatives, and that means I have dA over dt, which was 6, plus dB over dt, which is 4, and that would give me 10 feet per second, right? So again, if I think about it, the shadow is growing at 6 feet per second. The man is walking at a rate of 4 feet per second. So the shadow's actually moving for two reasons. The man is walking, so the shadow would have moved even if it wasn't growing at a rate of 4, but it's also growing, so the tip is moving at a rate of 10, right? And the last thing we kind of want to do in any word problem is check the answer, right? So does the answer really make sense? Is it within the expected range given physical or other reasoning, right? So sometimes an equation may give me an answer, but there may be physical constraints that make it not an acceptable answer. It may not fit within logic or physics, right? Even though it algebraically may work. So what we're going to do is revisit this problem. So the shadow will grow because the man is walking away from the pole. So the rate should be positive. Our answer was positive, so far so good. And the rate should be roughly the same as the walking speed, right? So it shouldn't be all of a sudden growing at 100 feet per second or maybe 0.2 feet per second. So it should be roughly the same. And it's, again, when I say roughly the same, it was 4 feet per second while the other one was 6. So they're close enough. They're not out of the realm of possibility, right? So the answers seem reasonable. Now, as we go through all of these different ones, of different related rates, they each require their own equation for us to consider. But a few things in here I want you to kind of remember. If you are drawing a picture, make sure you distinguish between what is a constant that is not changing and things that are variables. So even though I have a value here for 17 feet away, that was a variable. So we don't include that as a constant. We assign a variable for it. And if we need to plug that in, we'll plug it in later after we've taken the derivative, right? So as we take the derivative of an equation, this number should not be plugged in because it is a variable, right? If you plug it in and you take its derivative, it becomes 0, and that means it's a constant. Okay, so hopefully some practice will help you master this.